Good day, viewers. Welcome to our today's class. We are still on thermodynamic relations. So we are asked to derive the following relation on the board. The first one says the partial derivative of t all over the partial derivative of p, keeping s constant, is equal to t v beta all over p. The second one says the partial derivative of t all over the partial derivative of v, keeping s constant, is equal to minus t beta all over cv multiplied by k. So now let's go ahead and derive these relations. In order to derive these relations, first we are going to be making use of our Maxwell relations. So the Maxwell relation we are going to make use of says that the Maxwell relation we are going to be making now, this is the Maxwell relation we are going to be making use of. Now I can rewrite the right hand side of this Maxwell equation as the partial derivative of t all over the partial derivative of p keeping s constant to be equal to, I can write this right hand side of this equation to be the partial derivative of v all over the partial derivative of t keeping pressure constant multiplied by the partial derivative of t all over the partial derivative of s keeping pressure constant. Now what I have here is still the same thing with what I have here, because the partial derivative of t and the partial derivative of t here can cancel out, and I will be left with the partial derivative of v all over the partial derivative of s, which is the same thing as what is here. So it's more like I've not done anything. Now we are going to be making use of some relations. We know that Cp is equal to t into the partial derivative of s all over the partial derivative of t keeping p constant. This we know from our previous relation, that is our previous lecture, we have derived this. And also we know that beta, which is our coefficient of volume expansion, is equal to 1 all over v into what? Into the partial derivative of v all over the partial derivative of t keeping p constant. Now this is what we have. So what we're just trying to do here, in order to get our first relation, we are just going to find a value for this to substitute here, and also a value for this to substitute here. Now let's start with this. What we are going to do here first is that we are going to be taking the inverse of this equation. If we take the inverse of this equation, it's going to be nothing but 1 all over Cp equals to 1 all over T into the partial derivative of T all over the partial derivative of S keeping P constant. This is what we have. Next, we are going to be multiplying this equation, that is both sides, by T. To do that, we are going to have T all over Cp to be equal to the partial derivative of t all over the partial derivative of s keeping p constant. This is what we have. Next, come back to this equation. We said that beta is equals to 1 all over v, the partial derivative of v all over the partial derivative of t keeping p constant. We are going to make this term here, that is the partial derivative of v all over the partial derivative of t keeping p constant, the subject of this relation. That is, we are going to multiply both sides by v. If we do that, we will have v beta to be equal to partial derivative of v all over the partial derivative of t keeping p constant. This is what we are going to have. Now, if you look at this equation we have here and this equation we have here, is the same thing as what we have here. We have the partial derivative of v all over the partial derivative of t keeping p constant here, which is equals to this. We also have the partial derivative of t all over the partial derivative of s. Oh yes, this is what we have. This is equals to this, and this partial derivative of v all over the partial derivative of t keeping p constant equal to this. So we just substitute their values in this equation and we'll get our first relation. Now let's do that. So we have the partial derivative of t all over the partial derivative of p keeping s constant to be equal to this, which is this. That is, we have t all over Cp multiplied by v beta. This is what we have. If you multiply them, it's nothing but the partial derivative of t all over the partial derivative of t keeping s constant will become t v beta all over c. And this is what we have. So we have just gotten our first relation. Yes. So now let's proceed to derive the second relation. Now, in order to derive the second relation, we'll still be making use of our Maxwell equation, but not this Maxwell equation, although. So the Maxwell equation we are going to be using to derive, I can call this one. Maxwell equation we are going to be using to derive our second relation is nothing but the partial derivative over the partial derivative of s keeping b constant multiplied by minus. So this is what we have. So this Maxwell equation is what we are going to be using to derive a relation, this relation rather. So what do we have here? This is what we have. So I can rewrite this equation. I can rewrite this equation. That is the right hand side of this equation to be have the partial derivative of t all over the partial derivative of v keeping s constant to be equal to minus partial derivative of p all over the partial derivative of t keeping v constant multiplied by the partial derivative of t all over the partial derivative of s keeping v constant. Now this is what I have. This equation that you see here is of course the same with this, because the partial derivative of t can cancel the partial derivative of t just like as we did previously, and then we have this all over this is equals to this. So this is what we have. So next, we know that CV is equal to t into partial derivative of s all over the partial derivative of t keeping v constant. This we know. So what are we going to do? We are going to make this term the subject of the formula, but not just this term. We will need the partial derivative of t to be dividing to be all over the partial derivative of s. Now, in order to do that, we'll first take the inverse of this equation. If we take the inverse of this equation, what do we have? We are going to have, this is what we have. So next, what do we do? Multiply both sides of the equation by t. We are going to have t all over cv to be equal to the partial derivative of t all over the partial derivative of s in the constant. This is what we have. So now what can you see from here? We have partial derivative of t all over the partial derivative of s keeping v constant. We also have the same thing here. So we just substitute the value for this. So this Maxwell equation now becomes partial derivative of t all over the partial derivative of v keeping s constant will now be equal to minus the partial derivative of p all over the partial derivative of t keeping v constant multiplying t all over cv. Now this is what we have. So let's clean this next side of the board and let's continue. Let's clean this side. We need a substitution for this. That's the next thing. We need a substitution for this. Now, in order to get a substitution for this, we will be using first our cyclic relation for PVT. We'll be using our cyclic relation for PVT. Now, don't forget that cyclic relation for PVT has been proven in our previous videos. So we are not going to be proving it, we are just going to be writing the relation straight away. Now, the relation states that the partial derivative of v all over the partial derivative of t, keeping p constant, is multiplying the partial derivative of t all over the partial derivative of p, keeping v constant. It's also multiplying the partial derivative of p all over the partial derivative of v, keeping t constant. Everything is equal to minus 1. We have derived this in our previous relation. So what are we going to be doing? If you look at this equation, we are going to be using an equation that looks similar, a term that looks similar to what is here. We have the partial derivative of p all over the partial derivative of t. Now, if you come here, where do we have the partial derivative of t and the partial derivative of t? If you look at this equation, it is this. We have the partial derivative of t and we also have the partial derivative of p. So why not we make this term here the subject of this equation? Let's do that. If we make this term the subject of this equation, we'll be dividing both sides by this and this. To do that, this equation will become the partial derivative of t all over the partial derivative of p, keeping v constant, will be equal to -1 all over the partial derivative of v all over the partial derivative of t, keeping p constant, multiplied by the partial derivative of p all over the partial derivative of v, keeping t constant. And this is what we have. If we take the inverse of this, it's going to be nothing but the partial derivative of t all over the partial derivative of p, keeping v constant. This will be equal to minus the partial derivative of t all over the partial derivative of v, keeping p constant, multiplying the partial derivative of v all over the partial derivative of p, keeping t constant. This is what we have. This is what we have. So next, what are we going to do? Next, we know that k, which is our compressibility factor, or we can call it our isothermal compressibility factor, k is equal to -1 over v, that is k, which is our compressibility factor, into the partial derivative of v all over the partial derivative of p, keeping t constant. This is what we have. But don't forget that k is also pronounced as copper. But for the purpose of this lecture, we are just going to be using its alphabet base, which is just k. So next, from here you can see that we have the partial derivative of v all over the partial derivative of p, keeping t constant. This term I just mentioned is also here. So what I just do is to make this term in this equation the subject of this equation. If I do that, I will multiplying both sides of this equation by minus v. I will multiplying both sides of this equation by minus v. If I do that, I'll have minus vk to be equal to, I can just rewrite this thing as minus vk to be equal to the partial derivative of v all over the partial derivative of p, keeping t constant. This is what I have. Now I can substitute the value of this in this equation. I can substitute it. But before I do that, let me just name some equation. I can decide to name this equation equation 1 before I proceed, so that it will be easy for referencing. I can name that equation 1. So this is what I have. I'm just going to be substituting this value, the value of this, which is this equation. Now let me do that. This value, let's just leave it. Substituting the value of this, which is this in this equation, I'm going to have the partial derivative of t all over the partial derivative of p, keeping v constant, be equal to minus the partial derivative of t all over the partial derivative of v, keeping p constant, multiplied by the partial derivative of v all over the partial derivative of p. But now I said I'm going to be substituting this value, so I can just write it direct as minus v instead of this. So this is what we have. So next, we also know that recently I've just said that beta, which is the coefficient for our volume expansion, I've said that beta is equal to 1 all over v into the partial derivative of v all over the partial derivative of t, keeping p constant. This is what beta is. Now, if you look at this equation, we can make this that is here subject of this relation from here. If we do that, all we're just going to do is that we're going to take the inverse first. If we take the inverse, we have 1 all over beta to be equal to, I can just rewrite this thing here so that we'll solve properly. I said beta is equal to 1 all over v, yes, 1 all over v into the partial derivative of v all over the partial derivative of t, keeping p constant. Now, if I take the inverse of this, I'm going to have 1 all over v to be equal to v into the partial derivative of t all over the partial derivative of v, keeping p constant. If I multiply this equation by v, if I multiply this equation, no, I'm going to divide the both sides of this equation by v. If I divide the both sides of this equation, it implies that I'm going to have 1 all over beta v will be equal to the partial derivative of t all over the partial derivative of v being a constant. Now, what can you notice? This term here is the same as this term here. So I'm going to be substituting its value, which is 1 all over beta v, in this equation above. If I do that, the partial derivative of t all over the partial derivative of p, keeping v constant, will be equal to minus now from here into the value of this, which is still the same thing as this, that is 1 all over bv, that is beta v, multiplied by minus vk. If I do that, I'm going to have the partial derivative of t all over the partial derivative of p, keeping v constant, to be equal to vk all over beta, where v can go with v, and this value will become, now this is our equation 1, and I'm going to be needing this equation, so I'm just going to write it here. Equation 1 says the partial derivative of t all over the partial derivative 1, because we are going to be needing it to make reference. Equation 1 says the partial derivative of t all over the partial derivative of v, keeping s constant, is equal to minus the partial derivative of p all over the partial derivative of t, keeping v constant, multiplying t all over cv. Now this is equation 1. Now from here, so I can clean the equation 1. Of course, I can clean equation 1 here. Now I've divided both sides by v. Of course, you can see that v has cancelled v rather. So I have the t all over the p, keeping what? Keeping v constant, is equal to k all over beta. This is what I have. Now, if you notice, this is what we have rather. So I can take the inverse of this equation. If I take the inverse of this equation, I will have the p all over the t, keeping v constant, will be equal to beta all over k. This is what I have. Now, the value of what is here, the partial derivative of p all over the partial derivative of t, keeping v constant, is still the same thing as what is here. We have the partial derivative of p all over the partial derivative of t, keeping v constant. It means that I can substitute its value, which is beta over k, for this. If I do that, I'm going to be having, I can substitute it into equation 1. If I do that, equation 1 will now become the partial derivative of t all over the partial derivative of v, keeping s constant, will be equal to, have minus into the value of this, which is this, minus beta all over k, multiplied by t all over cv. This will be nothing but the partial derivative of t all over the partial derivative of v, keeping s constant, will be equal to minus t beta all over k v. Now this is our second relation which we are asked to derive. You can see this is of course equal to this. So we have derived the following relations. Thank you for watching and stay tuned for more videos.